Section: Introduction. In this section, we discuss the remarkable capability of large language models, LLMs, to understand complex concepts through their internal representations. This ability has led to the development of techniques like activation steering, which allows us to modify LLM behavior by adjusting these representations. However, we face a challenge. Current activation steering methods lack conditional control, meaning that when we add a refusal vector, it indiscriminately increases refusal rates across all inputs, limiting the model's effectiveness. To address this, we introduce Conditional Activation Steering, CAST, which provides more precise control over LLM behaviors based on context. We propose a new steering vector called the condition vector, which reflects specific activation patterns triggered by the prompt during inference. By comparing this condition vector with the model's activations, we can decide when to apply the refusal vector, enabling us to selectively refuse harmful prompts while still responding to safe ones. Our method maintains the efficiency of activation steering in terms of data, runtime, and computational resources, while enhancing controllability. This allows us to implement behavioral rules in LLMs without incurring significant costs. For instance, we can set rules like refuse if the input is about hate speech, or refuse if the input is not about legal advice, allowing for tailored responses without needing to optimize weights. On a technical level, we observe that different prompts activate unique patterns in the model's hidden states. We can extract these patterns as steering vectors, which serve as indicators for specific prompt categories or contexts, referred to as condition vectors. Next, we explain how transformers perform inference. These models process input tokens through multiple layers, transforming them into token embeddings. Each layer builds on the previous one, creating complex representations that culminate in predicting the next token from the model's vocabulary. We can influence model behavior at various stages, such as through prompt design or weight optimization. Activation steering specifically modifies internal activations during inference. This involves extracting a steering vector by comparing activations of desired and undesired behaviors, adding this vector to the model's hidden states, and then generating outputs based on these modified activations. In our approach, we enhance the basic activation addition method by introducing the dimension of condition, significantly improving the effectiveness of existing activation steering techniques. Section Summary. In this section, we introduce Conditional Activation Steering, CAST, a method that enhances activation steering by allowing context-dependent control over large language model behaviors, enabling selective refusal of harmful prompts while maintaining responses to harmless ones. We demonstrate that CAST can implement behavioral rules efficiently, addressing the limitations of existing methods that lack conditional control. Section: Conditional Activation Steering. In this section, we discuss Conditional Activation Steering, or CAST. A common issue with current activation steering methods is that they apply changes uniformly to all inputs, which limits their effectiveness. We demonstrate that we can create conditional behaviors by using two types of vectors, condition vectors and behavior vectors. The behavior vector is a one-dimensional vector that matches the dimensions of the model's hidden state and is designed to induce specific behaviors, such as refusal. By adding this vector to the layer representations during processing, we can predictably alter the model's behavior. We also determine which layers to apply the behavior vector to, and our approach calculates a unique vector for each layer since behavior representations can differ. The condition vector captures a set of instructions that we want to condition on, similar to behavior vectors, and it also matches the hidden state dimensions. This vector acts as a trigger, indicating when to apply the behavior vector based on the model's current state. We can choose which layer to condition, and when the condition is met during text generation, the behavior vector is added to all subsequent processing. To check if the condition is met, we use cosine similarity to assess the alignment between the hidden state and its projection using the condition vector. A simple thresholding function determines if this alignment is sufficient to trigger the behavior change. We focus on directional similarity rather than magnitude, and we apply a nonlinear transformation for more predictable outcomes. We can also implement multi-conditioning by breaking down broader goals into specific categories, allowing us to induce refusal behaviors for each category, such as adult content or false advertising. Our process for implementing conditional behaviors in large language models follows these steps. First, we gather contrasting examples for the desired behaviors. Second, we extract the behavior and condition vectors. Third, we identify the optimal points for intervention. And finally, we apply the steering. Importantly, the model itself does not undergo weight updates. The most time-consuming part is finding the right intervention strength and layers, but most of our experiments can be replicated within an hour, with the grid search being the main time-consuming aspect. We provide further details in the appendix. Section Summary. In this section, we introduce Conditional Activation Steering, CAST, which allows us to modify a model's behavior based on specific contexts by using condition and behavior vectors, rather than applying changes uniformly across all inputs. We detail how these vectors interact through cosine similarity to determine when to apply behavior modifications, enabling more nuanced and context-sensitive responses from the model. Section: Preparing Dataset and Model. In this section, we prepare our dataset and model. We need contrast datasets to extract behavior or condition vectors. For the refusal behavior vector, we randomly choose 100 instructions from the alpaca dataset and pair them with 100 typical refusal or compliance responses. This results in 10,000 contrasting data pairs for our analysis. We maintain this setup for the refusal behavior vector throughout our research. We also explore different condition vectors for our experiments. In one part of our study, we create vectors using SARI bench and alpaca data. When we need more data, we mainly use machine-generated content, including paraphrasing. We perform basic quality checks on the training datasets but do not apply further filtering, as we find the process robust against minor data changes. We manually verify every item in the test set to ensure its integrity, but we do not make any modifications. More details on data generation can be found in the appendix. Next, we extract steering vectors from contrastive examples, which are pairs of inputs showing the presence and absence of a target behavior or condition. We compute hidden states for both positive and negative examples in our contrastive pairs. The way we compute these hidden states varies between behavior and condition vectors. For behavior vectors, we average the hidden states of the suffixes, while for condition vectors, we average the hidden states of all tokens to get a complete view of the input. We then mean-center these hidden states and apply principal component analysis, PCA, to find the first principal component, which becomes our steering vector for each layer. In the next part, we focus on conditioning refusal by steering the model to refuse harmful prompts while complying with harmless ones. We generate 90 harmful prompts for each of the 45 harm categories, resulting in 4,050 harmful prompts. For each harmful prompt, we randomly select a benign instruction from the alpaca dataset. We then extract the harmful condition vector and use a grid search to find the best combination of parameters that separates the two classes of training data. Our results show that conditional activation steering effectively increases refusal rates for harmful content while keeping harmless prompt refusal rates mostly unchanged. This contrasts with standard activation steering, which indiscriminately raises refusal rates across all prompts. We also observe that conditioning has a dual nature. Changing the comparison direction allows us to intervene on the opposite set of hidden states. This gives us complementary control over the model's behavior. Additionally, our steering method provides flexible control, with the threshold modulating the alignment between the input and the harmful direction. Lowering the threshold narrows the range of hidden states that trigger the condition, while raising it broadens this range. However, we do not delve deeper into this aspect in our study, opting instead for threshold values that maximize the F1 score. Lastly, we note that unlike traditional weight optimization methods, conditional activation steering reaches a performance plateau quickly. This suggests that its effectiveness relies more on the model's existing representations and the quality of the data rather than the quantity of conditioning data. We also find that the time taken for condition vector extraction increases linearly with the number of samples, as it depends on the number of inferences needed to record hidden states. Section Summary. In this section, we describe our methodology for preparing contrast datasets to extract behavior and condition vectors, focusing on refusal behavior by combining instructions from the alpaca dataset with refusal prefixes, resulting in 10,000 contrasting data pairs. We also detail our approach to conditional steering, demonstrating how we can selectively increase refusal rates for harmful prompts while maintaining compliance with harmless ones, and discuss key properties of our method, including duality, modulation, and saturation. Section: Programming Refusal. Logical composition of refusal condition. In this section, we move beyond the broad idea of refusing harmful content and focus on creating more detailed condition vectors. We develop 5 example condition vectors based on categories such as hate speech, legal opinions, sexual content, health consultations, and crime planning to explore these concepts. Our experiments show that we can 1. Selectively adjust refusal behaviors for specific conditions and 2. Create complex refusal conditions by logically combining several condition vectors, allowing us to control the model's behavior programmatically. For our experimental setup, we start by randomly selecting 1,300 base prompts from the alpaca training set. We then paraphrase these prompts to include elements of sexual content, legal opinions, hate speech, crime planning, or health consultations, resulting in 1,300 prompts across 6 categories, including the original benign prompts. We divide this dataset into 700 prompts for training and 500 for testing in each category. To create a conditioning vector for a specific category, we use the 3,500 training prompts from the other 5 categories as negative examples and repeat the 700 training prompts from the target category 5 times for positive examples to balance the dataset. Next, we explore how to induce or suppress refusal behavior in specific categories. We start with a model that shows arbitrary refusal behaviors. Our findings indicate that we can indeed induce refusal behavior when certain conditions are met, demonstrating successful selective refusal. Additionally, we can remove refusal behavior from specific prompt classes by reversing the signs of the behavior vector. We also examine the logical composition of condition vectors. By combining condition vectors, we can create complex refusal conditions. For example, to induce refusal for both hate speech and legal opinions, we could implement a rule that states if either condition is met, then we apply a specific behavior. This multi-conditioning approach can strengthen existing refusal conditions, making the model more robust against harmful prompts. Furthermore, we can steer models to respond only to specific types of prompts, which is useful for creating specialized models, like a health assistant. Instead of refusing all non-health categories, we can create a condition vector for health and flip the comparison direction to refuse all other inputs. Our investigation also shows that this method remains effective for unseen prompt categories, as we tested additional harm categories not included in our original training setup. We found that constraining the model to refuse other categories works better for semantically distinct categories. Our analysis shows a positive correlation between a category's average semantic distance from others and the effectiveness of constraining to that category. This explains why constraining the model to hate speech is more effective than to legal opinions, as hate speech has clearer boundaries. Finally, we note that prompting alone is not an effective alternative for behavior steering. Our experiments confirm that conditional steering consistently outperforms simple prompting across most categories, highlighting the limitations of prompting in providing strong control over model behavior.